Welcome to my tutorial, which will be giving you an introduction to structural fire engineering analysis using Abaqus. We will be using the Gillie benchmark, which was published in 2009. My name is Michael Kluis, and I'm part of the Fire Engineering Research Unit at Stellenbosch University in South Africa. So why are we doing this? Well, modeling structures and fires can become quite complex due to a number of reasons. For instance, material and geometric nonlinearity, complex boundary conditions, and time temperature histories, which is essentially a fire. So the Gillie benchmark is quite nice because it incorporates all of the above modeling difficulties, but the actual structural model is quite simple, so it's easy to check. So over here we have the full reference in case you need to go check out the actual paper which was published in 2009. Alright, so let's go to Abaqus and let's get modeling. Okay, well, before we do that, I need to just quickly introduce the actual benchmark. I'm not going to read through it. You can pause the tutorial and just quickly read this and this, and have a look at this. Essentially, though, it's just a 1 meter long beam which gets subjected to an increase and a decrease in temperature with a constant load. Like I said before, you can get the full paper to read more about it. Okay, so we're going to start at the part and draw our section. I found that using a shell is sufficient to get a good correlation with the benchmark. So we choose a shell, we leave these as they are, approximate size of 5, and let's draw our beam. Give it the dimensions. So like I said, it's 1 meter long and it's 35 millimeters tall. Keep in mind your units. So I'm using SI units, which I find to be quite, which is a good way to do it. Alright, we can then stop that. So now we can move on to property and define our material. So let's call this steel. And we need to give it a Young's modulus of 207 gigapascal, and importantly, it's independent of temperature in this benchmark. So let's go 207 E9 and give it a Poisson ratio of 0.3. If you were to make it temperature dependent, you would just click this box and you get your temperature field over here. Then we've got our plasticity. So let's see what the benchmark says. It's 250 megapascals at 0 degrees and 0 at 1000 degrees, decreasing linearly. So we're going to use temperature dependent data. So the yield stress is 250 megapascal. That's when it starts to yield, and that's at a temperature of 0 degrees. Then the yield stress at 1000 degrees is 0, but you can't put 0 in here because for the FEM model or in a matrix, you can't have a zero yield stress. So we're going to put in a very small yield stress, which is essentially 0. And that's also a plastic strain of 0 and 1000. You can give much more complex material models here by just using a full table with many more plastic strains. So if you have a more curved elastic plastic relationship. And then finally we're going to give it expansion, which is quite important for fire modeling. So let's see what they say. It's got a coefficient of thermal expansion of 1.2 times 10 to the minus 5, which is again independent of temperature. So that's 1.2 E minus 5. Cool, that's our material model done. Let's create our section. Let's call it beam sec. It's a shell section, homogeneous. It's got a thickness of 0.035, and the material is steel that we just defined. And finally, we just need to assign our section. So we can give it a name. Let's call it beam hole, and we give it the beam section. Now we can move on to our assembly. Create an instance of our part. I always like to just shift it to the origin. Probably not necessary for this tutorial, but anyway. Cool, once we have our assembly, we can move on to step. So the way we're going to be doing this is using a static analysis with time steps, normalized time. So Firstly, we're going to have a mechanical step in which we apply our mechanical load, and that's just a static general step. And then another step, which we can call thermal step, which we'll then be using to do the thermal analysis. So in this one, it's important to use time increments. So what we're going to be doing is we're going to give it an initial time increment of 0.01. So this is over normalized time. And we're also just going to give it a maximum time step to make sure that the time steps stay quite small. And then let's just give a maximum increments of 1,000. Probably not necessary for this benchmark, but anyway, you don't want it kicking out if it does too many increments. Importantly, you need to make sure that nonlinear geometry is selected for both the steps. This is obviously very important for fire. What this essentially means is that it will just recalculate the stiffness matrix based on the geometry of every step and not based on the original geometry. Alright, so now we need to we're going to apply our boundary conditions, which is essentially a pin and a pin on either side with a spring. But to do this efficiently and well, we're going to be using reference point and constraints, which I found to be quite useful for bigger models especially. So let's do 2 reference points on either side of the beam. Let's change the names as well. So we go to assembly features, that's RP1. Let's just call this one RP left, or left hand side, and let's call this one RP right hand side. Cool. So we're going to be creating our constraints, which are essentially what the constraint means is that we're going to be taking this point and constraining it to this surface, so that we can apply a boundary condition at a single point, but that will then apply to the whole surface rather than applying a boundary conditions to a surface. So to create a constraint, you go over here, create constraint. Let's call this constraint left-hand side. The one that I found to work quite well is the coupling constraint. So it asks for the constraint control point. We're going to be using the reference point we just created, and let's give that a name. So this is a set name, and we can just call it the same as the reference point itself, RP left-hand side. I found that the constraint region type works better if you use node region, and then let's select the region we want to constrain. Let's call this end left-hand side. Done. Okay, so this is here are your options for what you want to constrain. Kinematic coupling constraint, these are the degrees of freedom. So essentially what this means is that these degrees of freedom at the end, left-hand side, will be constrained to these boundary conditions at the reference point. You can unclick these if you want to only constrain certain degrees of freedom, but we're going to leave all of them constrained. Alright, then let's just quickly do the same thing on the other side. So let's call it right-hand side, coupling. Click on there, give it a name, RP right-hand side. Node region. Click on the end, give it the name end right-hand side. Done. Alright, now we can apply our boundary conditions. So the boundary conditions are pinned on either side, and there's a spring which is 75% of the axial stiffness of the beam itself. So let's first do the pin on the one side. Let's call this left-hand side. We're going to be applying our boundary conditions in the initial step. It's mechanical, and we're going to be doing displacement rotation. So here, instead of clicking on it again, we can now go to our sets, which we've already made. We want to apply this to the reference point on the left-hand side. If you're unsure where that is, you can always click here, and then it will show you where it is in the model. So we're going to be constraining everything except rotation around the z-axis. Alright, let's create our right-hand side boundary condition. And in this case, we're going to be doing everything except the rotation, as well as the displacement in the x direction. So this will allow it to expand. Okay, now importantly, we need to apply the spring over here. So the springs are done in the assembly module. You can go to engineering features, springs dashpots. We're going to be using the second one, connect points to ground. So what that means is it will connect the point that you select to an infinitely stiff surface. Let's call this one axial stiffness. So we're going to be applying it to the right hand side, and we're going to be giving it a stiffness of 75% of the axial stiffness. So the calculation I did over here, it's simply 0.75 times AE over L, which gives you this. Keep in mind to work in SI units here, if those are the ones that you use to sketch your part. And importantly, we need to choose the degree of freedom, and we want that in the one direction. So that spring will be constraining movement in the X direction. Alright, our boundary conditions are done now. Now we can define our load. So in the Gillie benchmark, the load is a 4,250 Newton per meter line load. So there's many ways to apply a load in Abaqus. The problem with applying line loads on shells is that you can only do shell edge loads, which would work in this case, but if you were to sketch more complex sections such as I-beams, you sometimes struggle to do that. Also, the shell edge load follows the rotation of the part, which can become complex in fire if there's very large deformations. So the way I'll be choosing to do will be a surface traction over the side of the beam. You could also partition your beam and create a series of point loads, but in this case I'm not going to show that because I'd have to create a whole bunch of partitions, which is going to take some time. So let's do the surface traction. We're going to be applying our mechanical loads during the mechanical step. Surface traction, we choose our surface. Let's call this beam side. Doesn't matter which side because it's a shell. Alright, so here we can define our load. We're going to be using a general traction so we can choose any direction. The direction here we can use a vector, so it's simply, it asks you for the first point of the vector, so that's just the origin, and then the second point of the vector will just be, I'm just going to put it -1 here, so this is essentially going to mean that it's going to go straight down in the y direction. Cool, then the magnitude of the load, it's a simple calculation. You're just going to take the line load and divide it by the height of the section, which will give you a force in pascals. Sorry. So we're gonna, that's the magnitude, and we can just leave the amplitude as a ramp. Importantly, we're going to be defining this traction for the underformed area, so that means that no matter what happens to the geometry, it will always stay constant. Plus, we're going to unclick this, which means it will always be going down. Cool, that's our load sorted. Alright, let's do a mesh. Oh yes, importantly, we're going to need to create a set in the middle of the beam so we can extract the deflection at that point. So let's just quickly make our partition on the part. So we're just going to go to the part module and go tools, partitions. We're going to be doing the midpoint datum point, and let's do that at the bottom. And importantly, we just need to create a set in the assembly module so that we can name it when we extract that data. So let's just call it midpoint. Select that partition. Cool. Okay, now we can go back to our mesh module. Alright, so again, there's many ways to do the mesh, but the mesh that I found to work well for this benchmark is as follows. I'm going to seed the edges differently. So the ends, I'm going to seed by a number, and we want 6 across the height. Okay, and at the top, we're going to seed with an approximate mesh size of 0.02. Alright, and then we're going to apply our element types. I found that the linear element, but with full integration, works quite well for this benchmark. Again, you could use anything you want here and try and replicate the results. These are just the inputs that worked for me. Cool, then now we can mesh our part. Something doesn't look right here. I think I just forgot to mesh this side over here. Cool, there we go. Alright, now we need to apply our time temperature history. So how we do this is using a predefined field in the load module. So let's call this temperature. And this is going to be happening during the thermal step. So it's got a temperature there. We can choose our sets. We already have selected the whole beam, so that's this one over here. Previously made that set right in the beginning. And in the benchmark, it's a 800-degree temperature, linearly increasing and decreasing. So we're going to be using a normalized time period because we're doing a static analysis. So that's going to be 0, that's going to be 0, 0.5, and that's going to be 1. So, and it's got a magnitude of 800. So to do that, we need to do an amplitude. We need to create one. We're going to be using a tabular amplitude. It's quite simple. At time 0, the amplitude is 0. At time 0.5, the amplitude is 1. So that's going to be 800 because the magnitude is 800. And then at time 1, it's going to be back to 0. So you can, of course, apply much more complex time temperature histories just using this tabular format. It's quite easy. Cool, there we go. All right. And I think that's everything that we need to run our job. So let's create our job. We can call this just job 1. And then let's submit. So while a job is running like this, you can click on monitor. This is quite useful. And you can see what your job is doing. So what this shows you here is you've got some warnings. None of these warnings are really that important. And then over here you can see how these are the step time. This is where you are on your step, and these are the time increments, the size of your increment. There's also some other information over here. So this is quite useful to see what your analysis is doing and if it's working and when is it crashing. Okay, so now it's completed. We can dismiss. See our results. Let's show the stresses. Let's show plastic equivalent strain. And then what's quite nice is that you can animate your history so you can see what's happening over time. So you can see here how if you want to change the speed, you just click on this button here, change your speed here. You can also make it play once if you don't want it to loop. So in terms of what's happening here, first it's heating up and expanding, then we have a bit of plastic buckling, then it's deflecting, and then at 0.5, so that's halfway along the analysis, now we're starting to cool, and now it's actually recovering its thermal strain. So quite an interesting series of events, but obviously we need to extract this now and compare it to the benchmark results. So those results are in terms of the axial force as well as the deflection. So what I've done is I've just digitized those graphs and I put them into Excel. So here you can see these are the 4 results from the Gillie benchmark for axial force and for deflection. Alright, so we need to extract those two things from the model. Alright, so the way we can do this is using XY data, and it's an ODB field output. It's going to be a unique nodal output, reaction force. So reaction force in the one direction, that's the X direction. That's going to be giving us, we're going to be doing at the end, so that's an approximation of the axial force. And then we're going to be using the vertical displacement at the midpoint, so that's U2. And then we can use our set names previously to quickly get to choose where we want that. So we want that at the midpoint and the left-hand side where the boundary condition is. Again, if you want to see where that is in your model, you can just click highlight and you can see it's over there and it's over there. Cool, so this is Abaqus's view of results, which isn't always that nice. So what we're going to do is we're going to just export this to Excel using plugins, tools, Excel utilities, and then we choose the ones we want to export. So we want to export the reaction force at node 1, which is the reference point, and the vertical deflection at node 332, which is the midpoint. So click OK. Then you can just see where it book. Okay, wait. Sometimes you just have to export it twice for some strange reason. I'm not sure why. So let's just do that again. There we go. Okay, so you can see this is the mechanical step, and then this is the thermal step. So we're just wanting to start from the thermal step. So let's copy paste that into my Excel spreadsheet. So what I've done here is I've just written a formula which converts the normalized time into the appropriate temperature. So you can see how at 1.5, so halfway along the thermal step, it's 800 degrees. And then at 2, it's again 0. And then I've just converted the deflection to millimeters and the force to kilonewtons. And then I've plotted those results on these two graphs. So the solid black line is the results from our analysis that we just performed. And you can see how there's quite a good correlation with the results for the axial force and the deflection. There are variations, but this is due to any number of reasons: the mesh size, the way you apply boundary conditions. The quite large differences between most of the results and the ANSYS results. And I think I know maybe why it is, and I'll quickly show you what I think is why it's so different. I found, if you remember, that when we applied our boundary conditions, we made it fixed on the one side and pinned on the other side with a spring. But if we go back to our load and we make both sides rollers, so we take our left-hand side, make that a roller, and we take our spring and apply it to both sides. Okay, to do that, we just need to define a new set. So you go to your sets, click on both your reference points, right-click, Boolean operation, and we can go union. So that's going to make a new set which combines the two. Let's call that RP both sides. Cool. Now we can just take our spring, axial stiffness, and just change the region over which it works to both sides. Okay, so now we're going to have a spring on this side and on this side on rollers. So if we run this analysis now, again, you can click on monitor, you can see what's happening over here. Alright, there we finished. Can dismiss this to see our results. So again, it's quite a similar series of events as before, but again, we need to extract our results to see. So we're just going to extract the same results. Oh, importantly, now we can't extract a reaction force anymore because there's a spring. So what we just quickly need to do is, I forgot to do this, we need to go back to here. We need to change our field output requests. So what we need is that in the thermal step, you need to output the nodal force. So we're just going to click that quickly. If you want to actually get the temperature at any step, you can also do that over here. You just go to thermal and you choose nodal temperatures. Anyway, so we just need to quickly run that job again. Okay, in the time that it's running, I just want to re-emphasize that the way I've done it now is the way that worked for me to replicate the benchmark results. There are very many different ways. You could do it using a dynamic analysis, using other meshes, other ways of applying boundary conditions. This is not the only way you can possibly do it. All right, let's get those results. So the way you need to get a spring force is you're going to choose element nodal, n force 1, so that's the force in the x direction. And we're going to be doing that at the axial stiffness springs. Alright, we just need to quickly uncheck these two. Okay, we can plot that. Let's extract that force. And stick this into our graph. So that's for the force. And let's just quickly get the displacement as well. And click this. Unique nodal. U2. And that we want at the midpoint. Cool. Now let's just get the export that. Cool. So if I do that, you can see how the result matches the ANSYS results much better. So it's possible that when the original benchmark results were done, they applied their boundary conditions differently. They applied 2 springs instead of 1 spring. And the reason for the difference, I think, is that 2 springs in series actually change the stiffness. So you can see how the slope is less, which means that there's less of an axial force at a certain temperature or a certain expansion. So this might be one reason why those 2 results are so different. I'm not sure why the Vulcan is significantly different. But the first way we did it, like this, you can see how all the Abaqus results are very, very similar. And over here you can see as well how the deflection matches the benchmark results very well. Alright, thank you very much for this tutorial, watching my tutorial. I hope it helped you, and I hope it can give you a bit of a head start if you need to do any more complex structural modeling of steel or concrete or any material in a fire. Thank you very much.